By 2027, an 8-ton commercial passenger aircraft will fly 3,000 kilometers on a single battery charge, doing what Western aerospace insisted was impossible for another 30 years. That is not a projection sketched on a corporate whiteboard. It is an active production schedule, currently being executed by CATL, the largest battery manufacturer on Earth, in direct partnership with China's state-owned aviation giant, COMAC. For decades, engineers assumed electrifying flight was blocked by an unbreakable law of physics. Standard batteries were simply too heavy to lift themselves, let alone a plane full of paying passengers. Trying to power a regional jet with car batteries is like forcing it off the runway while carrying 8 full-grown elephants in the cargo hold. But here is the part almost nobody is talking about. This was never really a battery story. It is a story about who ends up controlling the sky. The physical limitation was never just about weight. It was also about fire. Traditional lithium-ion batteries max out around 250 watt-hours per kilogram, a number that sounds abstract until you realize it means the pack alone would weigh more than the payload it is supposed to carry. But the second wall was arguably worse. The liquid electrolyte inside a standard battery, the reactive chemical fluid that carries charge between electrodes, becomes dangerously unstable at high altitude and low atmospheric pressure. In a car, a battery fire is a catastrophe. At 30,000 feet, it is unsurvivable. The global aviation industry looked at these two constraints, weight and thermal volatility, and concluded they formed an unbreakable law of nature, not a challenge to be engineered around, a permanent ceiling. So Boeing and Airbus did what any rational company does when a wall looks immovable. They stopped trying to climb it. Billions of dollars got redirected into fractional efficiency gains on aging turbine engines, shaving a percentage point here, a percentage point there, while everyone quietly waited for a mythical solid-state battery that might someday solve the problem. Meanwhile, the economics underneath the entire industry stayed exactly as fragile as ever. Commercial aviation runs on razor-thin margins, and those margins are held hostage by the price of refined jet fuel, a volatile global commodity tied to crude oil markets, geopolitical conflict, and a sprawling logistics chain of tankers, refineries, and transport trucks. When fuel spikes, ticket prices spike with it. Airlines absorb the pain until they can't, and then passengers absorb it instead. Replacing that liquid fuel with a dense, rechargeable battery does not just clean up emissions. It severs the entire industry from the oil market itself, turning short-haul flight into something closer to a predictable utility than a volatile commodity gamble. While Boeing and Airbus kept polishing engines they already had, a completely different supply chain was quietly being built 4,000 miles away in southeastern China. To understand why this breakthrough matters, you have to go back to where the modern battery actually began. When Sony commercialized the first liquid lithium-ion cell in 1991 to power handheld camcorders, it kicked off a genuine consumer revolution. But it also locked the entire industry into a rigid chemical architecture that would eventually hit a hard ceiling. As researchers pushed that liquid chemistry harder, trying to squeeze more energy into smartphones and early electric cars, they ran straight into two serious problems. The first was structural safety. Cramming more energy into a liquid cell means thinning the internal separators that keep volatile components apart. One microscopic defect, one moment of physical stress, and the cell can trigger a self-sustaining chemical fire that cannot simply be smothered by cutting off oxygen. The second problem was slower, but just as fatal. Repeated charging and discharging causes microscopic, needle-like structures called dendrites to grow inside the cell. These tiny metallic spears eventually pierce the internal layers, causing short circuits that can destroy an entire battery pack in an instant. Faced with both problems at once, the industry concluded that liquid batteries could never safely reach the threshold required for commercial flight. So attention, and billions of dollars, shifted toward what looked like the obvious fix, the all-solid-state battery. Replace the dangerous liquid electrolyte with a rigid layer of ceramic or glass, and in theory, you eliminate both the fire risk and the dendrites. Western venture capital poured into solid-state startups throughout the 2000s, with automakers and aerospace firms signing exclusive deals and confidently predicting ceramic batteries would dominate within years. But there was a flaw nobody accounted for in the lab. Ceramic is brittle. As a battery charges and discharges, its internal materials expand and contract at a microscopic level, and rigid ceramic simply cannot flex with that motion. It cracks, separates, and loses contact, essentially tearing itself apart from the inside after only a handful of cycles. The technology that was supposed to save electric flight stayed permanently stuck in the lab. While Western engineers kept trying to force a brittle ceramic to behave like a flexible material, CATL's team looked at the problem from the opposite direction entirely. Instead of choosing between a dangerous liquid and an impossibly rigid solid, they turned to biomimetic engineering, studying how natural systems maintain structural integrity under extreme repeated stress. What they built was something in between: a polymerized condensed-state electrolyte, a semi-solid gel that actively adjusts the forces between its own polymer chains as the battery charges and discharges. Think of it like memory foam. Press down, and the material yields and adapts without cracking. Remove the pressure, and it holds a stable, unified shape. That is essentially what this electrolyte does under the violent stress of a jet takeoff, flexing without snapping, while completely suppressing the dendrite growth that destroys standard liquid cells. The numbers back it up. This architecture hits a verified energy density of 500 watt-hours per kilogram, comfortably clearing the 450 watt-hour threshold aerospace physicists calculated as the minimum needed to carry a commercially viable payload. For context, a luxury electric car that travels 300 miles today could swap in this chemistry and hit 600 miles without adding a single ounce of weight. Then there's the thermal performance. The battery operates flawlessly from freezing altitudes of -40 degrees Celsius to scorching tarmac heat of 60 degrees. If a localized short circuit occurs, the polymer network absorbs and suppresses the heat before it spreads, similar to a fire retardant wall containing a spark before it burns down the whole structure. And when the pilot needs a burst of raw power to force an 8-ton aircraft off the runway, the battery delivers an estimated 600 watts per kilogram, discharging instantly without dangerous internal heat buildup. Picture the difference between a garden hose and a pressurized fire hydrant. It's not just about how much energy the battery holds. It's about how much force it can release in a single violent burst. Rigorous testing has proven this architecture can sustain 1,000 to 1,500 full charge cycles, meeting the reliability bar commercial aviation demands. Developing the chemistry was only half the equation. The real bottleneck in advanced battery technology has always been mass production. Western solid-state startups kept failing not because the science was wrong, but because their rigid ceramics demanded entirely new, hyper-expensive manufacturing processes, things like isostatic pressing inside vacuum chambers. Building the factories alone would take years and billions of dollars they didn't have. CATL bypassed that trap entirely. Their condensed matter battery was deliberately designed to stay compatible with existing gigafactory production lines. Because it retains a small percentage of liquid within the semi-solid gel, the electrolyte can be injected using modified versions of equipment that already exists on the factory floor. No need to tear down the supply chain and start over. No need to spend years building specialized robotic assembly systems from scratch. In practical terms, scaling this technology costs a fraction of what the West's solid-state approach would have required. That speed is exactly why CATL has already completed flight verification on a 4-ton test aircraft, and why they are now actively scaling that same proven architecture toward an 8-ton commercial passenger plane by 2027. And the speed isn't just about manufacturing efficiency. It comes from the structure of the partnership itself. Because CATL is developing this battery inside a closed-loop joint venture with COMAC, China's state-owned aerospace manufacturer, engineers can optimize the airframe, the engine, and the cell chemistry all at the same time, inside the same organization. There's no external contractor slowing things down, no years-long negotiation between a battery supplier and an aircraft builder hoping to integrate a still unproven prototype. It's like writing the software and building the computer hardware simultaneously, instead of designing one and hoping the other eventually fits. The global aerospace industry has badly underestimated how fast this is moving. What started as a battery chemistry problem has already become a scheduled logistical reality. But the battery itself, as impressive as it is really just one component. The bigger story is what CATL and COMAC are quietly building around it. Here's the part almost nobody caught, because it didn't involve a flashy product announcement. Back in 2023, CATL quietly formed a dedicated, heavily capitalized joint venture with COMAC, officially named COMAC Times Aviation. This wasn't a normal vendor relationship, where a battery company hands over a hopeful prototype and waits years for approval. It was a complete top-down merger. The airframe, the chemistry, and the regulatory safety standards were all being written simultaneously, under one roof. They own the battery, they own the plane, they own the airspace. The entire approval pipeline is internalized, which means they can move at a speed the American FAA and European EASA were never built to match. To understand the scale of what that means, look back at the dawn of the jet age. When Boeing launched the 707 in the late 1950s, America didn't just sell an aircraft. It set the global standard, dictating airport infrastructure, fuel logistics, and international safety protocol, forcing every other nation to buy into a system designed in the United States. CATL and COMAC are running that exact playbook now, except this time, the West is the one standing on the tarmac watching it happen. We should be honest about the limits, though. An 8-ton aircraft flying 2,000 to 3,000 kilometers is not going to replace a wide-body jet crossing the Pacific. Long-haul international flight stays dependent on jet fuel for the foreseeable future. But here's the thing most people miss. The overwhelming majority of aviation revenue was never long-haul. It comes from high-frequency, short to medium regional routes, and that is precisely the market this battery is built to dominate. If this scales the way CATL intends, it won't just chip away at Boeing and Airbus. It will hollow out their most profitable domestic routes from the bottom up, while they're left defending a shrinking slice of expensive international flights. Zoom out, and this was never really about a battery. It's a full realignment of who controls the skies. Long-haul flight stays tied to jet fuel for now, but the high-frequency regional routes, the ones that actually keep airlines profitable, are exactly what's being commoditized out from under Boeing and Airbus. If this pattern feels bigger than you expected, hit like, subscribe, and turn on notifications so you don't miss what comes next. So here's the question worth sitting with. Which legacy aerospace giant feels this first? And how fast does the rest of the world get forced to fly on a standard it never wrote?